This video introduces TopNet, transformer-based object placement network for image compositing. Here's the problem statement. Given the background image and the foreground object, the goal is to find the best location and scale to place the object, so that realistic composite image can be generated. Existing works either generate candidate bounding boxes or apply sliding window search using global representations from background and object images, which fail to model local clues in the background. We propose to combine local features of the background and global feature of the foreground to generate a 3D heat map, indicating the compatibility of all the location and scales. Here's an example of our method generalizing on natural images. As for the architecture, we use the background and foreground image as input. We put them into two different encoders, which could be CNN or Vision Transformer. We combine the local feature of the background image and the global feature of the foreground image. Then we use another transformer to learn the correlation between them, and the output tokens are fed into a decoder. This decoder contains multiple upsampling convolutional layers to generate a 3D heat map. The spatial size of the heat map is the same as the background image, and it has 16 channels corresponding to the 16 predefined scales. Finally, we'll use the location and scale with the highest score as the placement bounding box to do the final compositing. One major issue here is the training data, because large-scale annotation is not available. There is only one small-scale dataset called OPA, which is manually annotated using COCO images. To take advantage of the large-scale high-quality images without annotation, like the Pixabay, we apply off-the-shelf in-painting models to generate training data. For example, here if we have an image like this, if there are more than 3 objects in the original image, we randomly pick up 3 object masks and apply in-painting to generate background image. And the original object location and scale would be the ground truth. If there are less than 3 objects, we will randomly add 1 additional object mask to prevent our model from overfitting the in-painting artifacts. Another challenge here is the loss function design, as the supervision is very sparse. Apparently, there is only 1 ground truth location and scale for each background and foreground image pair. The straightforward way is to assign a ground truth location as 1 and all the other locations as 0 on the heat map, or using a Gaussian distribution to have a more smooth heat map assignment. However, for most of the cases, there are multiple good location and scale combinations, and this kind of loss only allows 1 peak distribution on the heat map, like this. So we propose to apply a sparse contrast loss so that the ground truth location scale is optimized to 1 and the lowest score is optimized to 0. But the other locations and scales are encouraged to be lower than a certain threshold. So this would allow multiple peaks on the distribution of the heat map, like this. We first evaluate our method on the in-painted Pixabay dataset and the OPA datasets using the IOU between the predicted bounding box and the ground truth bounding box. Our method performs much better than the previous method. Here's the qualitative results on the inpainted Pixabay dataset. And here's the OPA dataset. We also test our Pixabay model on natural images without inpainting artifacts. And here's the result. As we can see, our method predicts good location and scale for the bird and the cat. We also conduct a user study based on these results, and the user study shows that our method has a better satisfactory rate than the other methods. We also show that the prediction of our model does not have large overlap with the inpainting mask, indicating that our model is not overfitting on the inpainting artifacts. Here's the visualization of the transformer attention map and the 3D heat map. To summarize, we propose a novel transformer-based architecture to model the correlation between the object image and the local clues from the background image, and generate dense object placement evaluation, with more than 10 times faster than previous sliding window method. We also propose a sparse contrastive loss to effectively train a dense prediction network with sparse supervision. Experiments on both manually annotated dataset and large-scale inpainted dataset showed significant improvements over previous state-of-the-art methods. It also generalizes well to challenging real-world cases. Thank you.